Hi everyone, good morning and welcome to our webinar. Today we are going to talk about the topic expanding the Honor OCS using SmartMod I/O, and the presentation should last around 40 minutes. It's going to be a short one today. As always, if you have any questions, please add them in the question panel and we will go through them at the end. That said, let's get started.
Hello and welcome to today's webinar. Today we will look at how to expand the Horner OCS using SmartMod I/O. Let's look at our agenda for today. We will start with a quick review of Horner Expansion I/O. We will then look at SmartMod and discuss the SmartMod I/O module lineup. We will then look at how to physically connect SmartMod I/O to the OCS, as well as how to configure the SmartMod I/O in Seascape. There will be demonstrations throughout, and we will finish with a Q&A session. First, let's look at some of the more common I/O platforms available to Horner customers so that you can pick the right I/O family for your application. We will start with the newest platform, which is the OCS I/O. If you have a newer application, then OCS I/O is most likely the best option for you. OCS I/O is a good fit whether you need a little or a lot of I/O in your application, and works well with nearly every Horner OCS available. If you need to add 16 to 32 point blocks of digital I/O at a time, then SmartSticks I/O is a good choice. SmartBlock I/O is best suited for high-end and high-performance analog, and SmartRail is ideal for high-density or high-mix applications. Where does SmartMod fit into this expansion lineup? SmartMod is an ideal platform if you just need to add a few channels of lower cost analog to your application. SmartMod I/O connects to the OCS over Modbus RTU, and every OCS supports Modbus RTU, meaning you can use SmartMod with any OCS product family. Most of the other product families we mentioned connect over CSCAN, which is the Horner proprietary CAN network, and SmartRail also has an Ethernet option. SmartMod instead uses an RS-485 type connection. Next, we will look at the lineup of SmartMod I/O options. Today we are focusing on analog, as it is the best way of utilizing SmartMod. However, there are also some digital I/O options available. There are many different options with ranges of 0 to 20 milliamps of voltage inputs, plus or minus 10 volts, as well as some RTD and thermocouple temperature sensors, which are available in 4-channel and 8-channel type options. These modules also have roughly a 15-bit resolution. The analog outputs also have 2-channel, 4-channel, and 8-channel options. Now let's look at the connections on a typical SmartMod I/O module. Here we have a 4-channel voltage analog input card. On the left, we have the I/O terminals. These will vary depending on which module you have in terms of the specific I/O connections that you're going to make. On the top right is the Modbus connection, which is typically 3 wires. We have a twisted pair data plus and data minus, as well as a common terminal, which is used for a ground reference. So typically you will have 2 twisted pairs, with 1 pair for data and 1 other conductor used for common. In the bottom right, we have the power input, which can support 12 and 24 volt input voltages. For the physical connections for RS-485, we will use multiple twisted pairs wiring for our signal pair and signal common. Cat5 or other category cabling can also be used here, and can be a good choice if you're simply connecting a SmartMod module to an OCS in the same enclosure. We could also cut off one end of an Ethernet-style patch cable and then use 3 of the conductors to wire up the SmartMod. We have shown how to do this in the table on the screen, including the color codes if you were to use Cat5 cabling. For RS-485, there is a 100 ohm termination required on each side. For RS-485, there is a 100 ohm termination required on each end. On the module end, you could use a physical 100 ohm resistor between data plus and data minus. On the OCS end, some models use a dip switch for termination for RS-485, whereas other models have a system menu entry for setting termination on the OCS, which will be easier than dealing with resistor on the OCS side. Now let's look at how we would configure the SmartMod. SmartMod modules are RTU slaves, which means we need to configure the OCS as a Modbus RTU master. We recommend that you use the default serial parameters, as they will be fast enough for most analog applications. These default parameters are 38400 baud, no parity, 8 data bits, and 1 stop bit. Any configuration that needs to be done, as well as reading data at runtime, is done through Modbus registers. This configuration data and the I/O data is mapped to Modbus holding registers. In the case of the thermocouple and RTD, there is some diagnostic data available in Modbus coils, specifically open circuit data in case one of the thermocouple or RTD fails open. Next, we will look at some key Modbus registers for interfacing with SmartMod. If we are using RTD or thermocouple sensors and we need to configure the sensor type from the default, then we will write to Modbus holding register 40011. The first and second charts on the screen show the different decimal values that you would set for different sensor types. The DAC007 or DAC107 modules are configurable for both current and voltage. If current isn't what we need on each channel, then we will write to Modbus holding register 40014 on those modules to set current or voltage. For reading or writing the analog data, we will use holding register 40015. So if we have two channels, we will use 40015 and 40016. And if we have 8 channels, then we will use registers 40015 to 40022. If we are using RTD or thermocouples, and we want to take advantage of the fact that the modules can detect an open circuit, then we will read Modbus coils 1 through 8. In most applications, we will just have one SmartMod connected to an OCS. However, if we have more than one module in our application, then we will need to change the default Modbus ID for all modules except the first one. We do this by writing to Modbus holding register 40007. Now let's look at an example configuration where we need to add 8 channels of thermocouple input into our application. So we might need to use a SmartMod THM200 module that has 8 thermocouple inputs. We may need to use Type K thermocouples here, which is not the default for that module, so we will have to set the type to Type K. We will do this by writing to holding register 40011. Then the temperature values that we read will be coming into Modbus holding registers starting at 40015 to 40022 in 10th degree Celsius increments. So if we want to leave these values in degrees Celsius, then we will convert that analog value we read over Modbus into a floating point value and divide it by 10. If we want to convert them to degrees Fahrenheit, we will take that Modbus value, convert it to floating point and divide it by 10, then multiply by 1.8 and add 32. Next, we will look at how to configure SmartMod I/O in Cscape. While we're in Cscape, we always start with the Modbus configuration, because that's how SmartMod interfaces with the OCS. To do this, we will select Hardware Configuration, then go down to Serial Ports and select Config. This is where we will find our Modbus RTU. Most OCS have 2 serial ports, MJ1 and MJ2. Some may also have a third port, MJ3, and RS485 is available on all of these ports. For our demonstration, we are configuring a micro OCS, so we only have MJ2. From this drop-down list, we have selected Modbus Master. We then have 3 levels of configuration. First, we will look at the network level. This is where we set a Modbus RTU as our protocol, as well as our serial parameters. Here we have our serial ports configured to the default settings, and we will keep these as they are. We will also leave the number of retries as the default. We have adjusted the timeout, which is the amount of time we will wait for the OCS to respond, to 1 second or 1000 milliseconds. So those are the configuration options we recommend for the port configuration. Next, we have the update scan, which we will leave as automatic with an update interval of 0. We have also reduced reacquire time to 1 second. So if we don't get a response from the SmartMod, We will retry 2 more times. We will take the unit offline, and then we will repeat the process 1 second later. Under Disabled Network, we have assigned an optional type variable as a disabled network function. So when this bit turns on, it will temporarily disable the Modbus, which acts as a Modbus reset. We also recommend that you use the SmartMod master status, which is 4 double integer values, the first of which we have assigned to a double integer based array. The first value will tell you in milliseconds how long it's taking for the OCS to pull the SmartMod I/O module. The second value tells you how many no responses the OCS is getting. The third value will tell you how many bad responses the OCS is getting, and the fourth value will tell you how many good responses the OCS is getting. So at runtime, you want to see the fourth value incrementing up on a continuous basis, and the second and third values hovering near 0. Next, let's look at the device level configuration. We have already added our SmartMod I/O here. We will double click this and look at our settings. We have assigned a name for our SmartMod here. The default ID for SmartMod is 1, which we will keep as is. We would only need to change this if we had multiple SmartMods, but in that scenario, the first SmartMod would still have an ID of 1. For the device type and mode, we've selected Modicon, 5-digit addressing, and the device supports all the function codes. For our demonstration, we have not added the disabled device variable here, which is Boolean type, because we have only one module. We have also not enabled status for this module. Next, we will look at our scan list. In this case, we have 3 entries in our scan list because we have a thermocouple module. Our first entry is accessing Modbus holding register 40011. This is a read-write variable which sets the type of thermocouple that we are using in our application. Here we are using type K, which is not the default, so we will write to this value in the analog register periodically. We have chosen pulled read-write init, so at power up, the OCS is going to write the value to make sure it's set properly to the value that the OCS wants, and then the OCS will go back to just reading that value and making sure it matches. Our next entry in our scan list is where we are reading our 8 channels of data. We have a Modbus holding register of 40,015. The length represents how many channels we need to read, which is 8. So we are reading these into an integer-based array that has 8 values in it. We have put the starting variable value here, which has an index of 0. This is a pulled read because we will only read these temperature inputs, we won't write them. Because this is a thermocouple or RTD module, we have the ability to read Modbus coils that tell us if any of our sensors are open circuit or not. We will take advantage of this, so we have assigned a Modbus coil starting at 1 with a length of 8 because we have 8 channels, and we have assigned this to a Boolean variable array with the first entry on the array listed. Once again, this is a pulled read because we don't need to write this data. Now we have done all our configuration, and next we will look at the screen we have made to display our temperature values in the graphics editor. Here we have our 8 temperature values. We have chosen to display these in their native format, so we have selected signed decimal, as these temperatures could also be negative values. These values will be returned in 10th degree Celsius increments, so we are displaying the data we are reading in directly with a decimal point, the location, and then adding the degrees Celsius unit. We are doing this for each of the 8 channels, with each having a different array member. We also have our open circuit coils here that are reading in and have also been assigned to a Boolean style array. So if any of our sensors are open circuit, then these pilot lights will turn red. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, I'm back. Since we don't have any questions so far, let me jump into the agenda. I hope you all can see it now. Starting next week, we will hold webinars based on Seascape 10. So the next webinar will be on the Seascape 10 user interface. And the following is about the Seascape 10 program downloads, and followed by Seascape 10 graphic editing and Seascape 10 and Canvas. If you want to participate, please register on our website. I believe that's all for today. Thank you all for your time, and I hope to see you in the next webinar. Have a nice day, everyone.